in case others are out, they can actually hear us later. So at A, it's fixed in both directions. Okay, it cannot move either vertically nor horizontally. Okay, it cannot move neither vertically nor horizontally. At B, though, look at the support at B here. This means that this object cannot move vertically, but these rollers show that there's no restriction to horizontal motion. So when we see the setup, mind you, again, you're going to do homework on this, and then I told you I'm going to give you a quiz on this. So make sure you're focused for sure here. You have a reaction that prevents motion vertically here, and we could actually call that RAY. And then we have a reaction that prevents horizontal motion here as well, but we can call that RAX. So I'm going to start by looking at the free body diagram of the whole system. Okay. So for the second part, I've got RB in the y direction. That's preventing motion vertically. Now, what did I talk about with torque? When we talked about moments, we said the sum of the moments about a certain point. We did that whole thing in forces. Anybody remember from the last example? What was the reason for using moments and stuff? For using moments? Oh, thanks, Coach. No problem.
Taking my class, Coach.
You right? Good. Oh, I thought you were limping your foot. Oh, gosh.
No, I'm good.
Where's your glasses? You always wear glasses.
Right here.
Okay.
Right here.
All right. Was Trooper with you by any chance? No? Is he not here today?
No, he's
Oh, he's not here today. Okay. So we have 3 reaction supports, but the problem is this. If I do the sum of the forces in the x and the sum of the forces in the y, that's how many equations? Just sum of the forces in the x, sum of the forces in the y. Just those 2 things. That's 2 equations. But how many unknowns do you see in the diagram right now? 3. So I need 3 equations to solve for 3 unknowns. That's the rule that I always remember. The number of equations needed is based on the number of unknowns. So I need a 3rd equation, and that's where we do the sum of the torque, or moments, about a point. So we assume that the bridge is not rotating if it's in equilibrium. The whole idea is to determine the reactions if this bridge were in equilibrium. So we assume no rotation. So what we can do is we can say the sum of the moments or torques about point A is equal to 0. Why am I choosing point A? Gus, you remember this?
Is it just because you could do both and you won't need to solve for B?
You have it backwards, actually. You have the right idea, but it'll eliminate the other 2 and you will solve for B, actually. Remember, how does a torque come about? It's a force applied at a distance and angle. Both distance and angle. Very good. So if I look at the torque at point A, RAY and RAX are acting at point A. How far away are they from point A? Physically, how far away are they? What number?
20 feet.
How far away from point A? What is it, Will? 0. They're on point A. So when I look at the torques for this, I won't have to worry about RAX and RAY because they're not acting at a distance from point A. That's the reason I choose point A. Whatever point you choose to do the moments about, it eliminates the forces acting on that point. So I see that there's 2 forces acting at point A, so I sum the torques at point A on purpose because these 2 will both go to 0. Because I'm going to take this value times the length away, 0. This value times the length it is away, which is 0. And then this value times its length, which is 20 feet. So this is the only force that will come about from that equation. So the first equation is going to become, again, 0 equals, well, I'll put the torques in first. So let's first look at torque from RAX. So it's going to be RAX times the length it is away, which is 0. Times the sine of the angle, which is the sine of 90. So this whole thing is 0 pretty much. I'm showing it, but it's 0. RAY times the distance it is from the rotating point, which is point A, which is just, again, 0. Times sine of 90 also. And then finally here, RBY, we have plus. Now in this case, RBY is going to cause what kind of a rotation? RBY, what kind of rotation would it cause? Clockwise or counterclockwise?
Counterclockwise.
Because I think about, good, as A is the fixed point, take your pencil, hold it at point A, and literally apply a force like this. That'll turn it which way? Counterclockwise. And counterclockwise, if you don't remember, is positive for torque. Okay, so RAY would have been positive. RAX would have done nothing really. I should actually put, sorry, that's the sign of, in this case, that would be the sign of 0, not 90. And I'll explain that one in a second. Let's make that a sign of 0. Right here, change that to sign of 0. Okay, so the last one again is RBY, and that's going to cause a counterclockwise torque. That's why it's positive. Times the distance away, which is 20, times again the sine of 90 degrees. Ernest?
Why is it, if it's x, why is it sine? Because wouldn't it be cosine?
So remember, this is always, the formula for torque from physics last year was always R times F times sine theta, and theta was the angle between these two vectors, R and F. So if I think about this, ready? I'll use blue to help you. So for this one right here, this is where the actual point, or the force RBY is applied, right?
Yeah.
The direction of the force is up and down. The direction of the distance is left to right. The angle between those two vectors is 90 degrees.
So
that's where the 90 comes from RBY over here.
Okay.
And the same thing goes for the next two. This is the force applied. The distance away technically is like left to right. So again, this is like a 90-degree angle here for this one. But RAX is the one that's the most interesting. Here's RAX. Watch. So RBY is acting at a 90-degree angle, the distance from the fulcrum. RAY is here, not doing anything. It's acting on the fulcrum. I can't generate any torque. RAX is acting like this. You see what I'm saying? Look at the diagram. We're pushing on the hinge. It's not going to cause any rotation because the angle between the vector F and the vector R is just 0 degrees. So that becomes the sine of 0 degrees, but it's also because it's on the actual fulcrum and there's no distance between it. So it's 0 for two reasons actually here, right? So actually, check this out. I can apply RBX, and that would look like this. And that would also cause 0 torque, right? Again, RBY is this. Think about the bridge. This is A, this is B. RBY is this, and it does apply torque. It causes the bridge to rotate. This is the bridge. And then RBX would not cause any rotation. Because again, the vector R is from here to here. The force vector is also here in this direction. So these are collinear. These lines are on top of each other. The angle between them is 0 degrees. So if I had, again, if I had an RBX this way, it would also cause 0 torque because it doesn't cause the bridge to rotate. Think about the bridge rotating about point A. Okay, about point A. Again, if I suddenly applied a force here called RBX, it's not in this diagram, I don't have to worry about it. RBY is, and RAY is, but RBX is not in the diagram, but it wouldn't matter. Think about it. It wouldn't cause a rotation this way. It wouldn't cause a rotation this way. So RBX wouldn't even cause any torque, so it wouldn't matter if I had it there anyway. But I don't, because these are on what we called rollers. Remember, this is a roller fixture. This is a pin fixture. This is a pin. A pin applies a force in two directions. A roller, though, only applies a vertical restrictive force, not a horizontal restrictive force. Yes, Jake? In this case, it wouldn't matter, because the sine of 0 is 0, the sine of 180 is 0. So it wouldn't make a difference. Okay, and this whole thing is equal to 0. Remember, the sum of the torques, we're assuming the bridge is not rotating, right? If it's in equilibrium, so we set the sum of the torques equal to 0. Now, in reality, we have to consider the forces at the top, because they act at a certain distance. So I have to include them in here as well. So because these other forces cause no torque, I'm going to erase them for now. I can't erase, of course. This app doesn't allow that. These go to 0 here, but I have to include the torque that comes about from these two forces that are applied. So this is where it gets a little bit tricky. So you really got to focus and bear with me here. Okay, I'm going to step you through a process that's a little bit easier than using angles and a lot of these angles here like we're going to do for the nodes in a minute. For these forces up here, I'm going to show you a little technique called translation of forces. And the idea, I saw your hand. Can I keep going or you want me to stop?
Yeah, I was just gonna ask. So we're always gonna not cancel out, but just forget or ignore the points at the reactions at the point.
Correct. The point at which we're rotating about, which we talked about here, we called it A.
Yeah.
Those forces are no distance from A, so the distances are always going to be 0.
Okay.
So these we can ignore. I showed it for today just so you guys can see it, but these you can pretty much ignore.
You said it was called translation of.
We're going to talk about translation of forces now up here. And what you can do, which is interesting, is you can take the force and slide it along the direction of the arrow or opposing the arrow direction until it gets to a location where it would make a 90-degree angle with your lever arm R. So let me explain. So take the 10 kip force, see the 10 kip force, extend the arrow in the other direction here until you can make a 90-degree angle with what we're calling the lever arm R. And that's the distance that we're going to use for torque. Instead of using sine and cosine and having to deal with that, it'll be the same answer, I promise it would. Okay, we're going to use that distance R there. And we're going to have to figure out what that distance R is, which is really in the end, it's given in this case, it's given as 10. Which will be a little bit easier than having to figure out, ready? We'd have to first find the length of this member and then use sine and cosine to worry about it. And it's like, you know what? I know that this length is really the R value, but I'm going to call this the R value instead. And it does work. It's translation of forces. You're allowed to do this. Yes?
Why can't you use a Pythagorean if you want?
You could. You could say this is 10 here, and this is 10 here. So this is 10 radical 2. So 45, 45, 90. Then, ready? You have to take this 10 radical 2, which is now the distance away, times the force of 10 kips, times then, again, the sine of 45, which would get you back to this exact value of R in the end. So what I'm showing you is more of a shortcut, if you will. But you could use that if you want to. You absolutely could. Okay, so I'm going to use this as the R value now, and that's going to go in here. Right, that's going to go in there. The F value is 10 kips. That's going to go in here. And the angle now is 90 degrees because I've translated the force on purpose to make it 90 degrees. Okay, it's a useful technique. I didn't do this in high school. I learned it in engineering, in like structure class in college in my freshman year. It's translation of forces. Very useful to do. So for this problem now, again, I still have this part of the torque right here, but I have to add on to that the torque that's generated from the 10 kip force. And the 10 kip force is at a distance of 10 feet away. The force itself is 10 kips, kilopounds. It's 1,000 pounds. Times the sine of 90. Now, which way would that force cause this to rotate? Again, take your pencil. Your pencil's here. Now imagine if the pencil extended into the bridge as a structure up here and you pushed on this piece of the structure. Would it cause it to rotate this way, or would it cause it to rotate this way? If I push on the structure here, yeah, it should be clockwise this time. And if you're not sure of that, take something that has some 3 dimensions to it, or 2 dimensions to it, not like a pen that has a line. Push here at the top, which is kind of what we're doing, right? Imagine, or take the bridge like this, sorry. Imagine this is your bridge. Push here. That's what we're doing. And it's going to cause it to rotate clockwise. Clockwise is a negative torque. So I should apply a negative sign in the front of this.
Do you know if your laptops are Java updated?
Don't use Chrome. It'll work. Go back to use Firefox
Yeah,
or Internet Explorer. Sorry, it'll work. But you can borrow mine if you need them, but they're not Java updated.
Okay, but it,
Java doesn't run through Chrome anymore. So if you're trying to open something in Chrome that runs Java, it won't work. So, Matt told me last week, because I was trying to update Java, and he's like, don't even do it, it doesn't make sense. And I was like, all right.
Internet Explorer
Internet Explorer or Mozilla, I think, works
or
too.
Edge or whatever.
Edge, yeah, it's Edge now. It's Edge.
All right.
Yeah. So we have the torque generated. Yeah, Mike, go ahead.
I was just gonna ask you another question. Do you American building companies, do they use standard measurements or measurements? I know they use.
I think they use standard measurements, like kilopounds and stuff, yeah. Yeah, I would say most do.
Because when other countries look at American architecture.
Yeah, I mean, in college, honestly, we use both all the time. In engineering school, at least, you always use both. Just because you have to be, just aware of both and be able to use them. It's really no difference. It's a matter of converting a lot of things,
With the 10's the R. Is it because of like how did you know?
It's the height right here. It's given in the diagram.
I didn't see that.
It's all right. Yeah, it's not
I thought
obvious.
it was
That's the
10
height.
KI. Oh, okay.
Okay.
Got it.
So this R here is really just 10 feet.
All right. And so
That's why I did the translation of forces, because I have that dimension already, right?
Yeah.
If
Also,
not,
just replace
I would have had to find this dimension right here, which would have been R. Then I would have had to use, so this is R, right? That's the force right there. I would have had to use theta, which would have been right there, right? And I had to use RF sine theta for that. And you can do that. That's totally fine. But I'm just like, you know what? Like, take a shortcut if you can.
Got it.
And translation of forces is something that, if you know that and you study structural engineering or architecture, your teacher would be impressed probably coming into it. Because I never learned this in high school, So I'm trying to give you guys just a little bit of like insight into what some of the stuff we did was.
So this basically just kind of replaces.
It replaces having to worry about the length of R and the actual angle, because you'd have to calculate that angle. And that angle turns out to be 45, and you can kind of see that if you did the work. It's 10 by 10 by whatever. So that angle would be 135 because it's 90 plus the 45. But in the end, it just makes sense to do it. So these are notes right out of my college text for this course. I'm not, like, it's not, I mean, the title of the book, this chapter is called Analysis of Planar Structures. So I took a lot of your notes that I have like little sections for out of textbooks. Let's see if I have the name of the text. No, I don't have the name of it anywhere. So all these figures and stuff, I pulled them out of just an old textbook I used in college. I had the PDF of the textbook in college. I don't think I got to record. What you'll call is a counterclockwise rotation. Okay, the 15 kip force. You're going to add on to that, or you were just saying the same thing?
No, I was just
Counterclockwise, very good. And counterclockwise is positive, so that one is going to cause a positive torque now. So that's going to be a positive in the front of this whole thing over here, and we put a positive sign. Okay? So my equation inherently is becoming this entire thing, right? You seeing what I'm doing? The equation is really just this entire thing that I'm going to use all these forces for. The two applied forces at the top node, and then the RBY on the right. RAY and RAX, they don't matter. So the 15 kip force, translated again. Translation of forces, extend either side of the vector until you make a 90-degree angle. Until you make a 90-degree angle with something that you know a dimension of. So look, keep extending this down. There's the 90-degree angle. And again, my distance will be 10 feet again. I'll point to where I was showing just now. So again, take the force here, continue to extend it down like this, keep going, keep going, keep going until you meet another member. And now, because we know this member is 20 in length, and this is symmetric in size, we know that this will be 10. So I can use a lever arm of 10 and a sine of 90 again, and just use a 15 kip force. So it's going to look very similar, but it's going to be a positive, and it's a positive 15 kips times a distance again of 10 feet, again times the sine of 90. So, for the last time, yes, you can absolutely calculate the distance from here all the way to here, and that could be your R value, right? This is your R value. You can do it this way. And then if this is the force here, and this is the R, and this angle again would be 135 degrees. So you could have done it that way again. Doesn't matter. Mike, last year with Mr. Donachek, I know he did a lot with trig and deriving all the sine and cosine of every value, right? So you'd probably be more comfortable with finding this length here and then using the angle. So if you want to do that, that's fine, because I know that's the way he did it. I always see his notes for that. But I'm just showing you other ways, so feel free to use this too. And now at this point, look at the equation. How many unknowns do you have? Just one, RBY. Okay, Jake, go.
So you just replace the first RAX and the RAY with each of those kips.
I didn't replace them. I recognized that these were zero. I just ignored the kip forces in the beginning. I didn't really include them when I did the original analysis. The original analysis is what's in blue, what's circled in blue. That's what should be there. I'm showing you that these don't generate torque. Okay, but there are 5 parts to the left side of this equation. Think about it. How many forces are applied to the bridge right now? 5. RAY, RBY, RAX, 15 kips, 10 kips. So you see how there's 5 torques there?
Yeah.
I just didn't have room to put them all in one row. That's why it's on the second row there.
I'm just confused. Why did you color code it blue?
Oh, I just switched colors. I don't know. It was just a stupid move. I was just showing you the 2 different forces. No rationale behind the color coding. What I circled in blue, though, what I'm saying, Jake, is what's left over in the equation that you have to solve. But there are really 5 torques, because there are 5 forces. But these 2 forces right here don't really generate any torque because they're acting on the rotation axis, like I showed with the door, right? So these go to 0. So really, if I was doing this and I wasn't teaching it, I was doing it myself for homework, I would only focus on these 3 forces that cause the 3 torques shown in the equation. Yeah? Okay, the other ones don't really matter, so I don't really care for them. And again, RBY is a positive torque, 15 kips is a positive torque, because both of those caused counterclockwise rotations. If you want to label the diagram with that, that's fine. Label that it shows counterclockwise for both of those cases. And then the 10 kip causes clockwise rotation. That's why that one was negative. I have a junior, I told you, who said, you know what, just think of counterclockwise as 2 C's and a positive sign as 2 slashes. Think of clockwise as 1 C and a negative sign has 1 dash. It's a good way of remembering which is which, unless you just memorize. But sometimes mnemonics help, right?
Could you, in solving it, like, could you just cancel out, like, 10 feet and sine 90?
Well, sine 90 is in all the terms, so that could drop off for sure. And the fact that sine 90 happens to be 1 also makes it. But 10 feet is not in all 3 terms, right? So I could divide everything by 10, but that would leave a 2 behind over here, wouldn't it?
Yeah. I was just thinking because, like...
That's fine. I mean, instead of multiplying out, you could divide everything by 10 to start. That's a good point. Ernest recognizes that everything has a 10 in it. There's a 10 here, a 10 here, and then 20 is really 10 times 2. So I could divide everything by 10 if I want to. Sure. You could also just multiply the numbers because the numbers are pretty easy, right?
Yeah,
It's 15 times 10 is 150 minus 100 plus 20 RBY equals 0. Okay, it's going to be 50 then, right? Equals, and I'm going to move the 20 RBY over. Just makes sense to do it all in one step. 150 minus 100 is 50 there. And then divide. So look at this. Interesting. I talked about this already. We're getting a negative answer now. 50 over 20 is just going to give me 2.5. My units were kips earlier, so I'm going to keep the same units. But it's a negative sign. What did I talk about when you get a negative answer? What does it actually mean? And this is not a negative answer in the member, which would mean compression. I know, I saw both your hands jump up. If you get a positive answer for the member force, it means tension. For the member force, a negative answer means compression. What does a negative answer mean at the reaction?
Does it just mean it's going to rotate clockwise?
Careful, you're on the right track. No, it was originally written as counterclockwise, so he's on the right track. But it's not going to rotate clockwise. You switch the direction of the rotation, right?
Yeah.
But I'm telling you that the force is the opposite of what it should be. So what should you really do? You switch the direction of rotation.
Switch the direction of force?
Yes. RBY, it turns out, in our diagram, everybody look at the diagram, we drew RBY up, didn't we?
Yeah.
But think about these forces. Analyze it. Physically makes sense. Isn't this pulling it up, guys? Look. Isn't that pulling it up?
No.
So this bridge is naturally going to want to move up because this is pulling up. So which way does RBY have to pull to keep it in equilibrium? It's got to pull down. It's not actually rotating clockwise, though. It is generating a clockwise torque. What he said was it'll rotate clockwise. It is not rotating clockwise. So what we have to recognize is that when we get, write this down in words, when you get a negative reaction force, it means that the reaction force was drawn in the wrong direction to start. Again, when you get a negative reaction force, it simply means that the reaction force was drawn in the wrong direction to start. Now, please, you don't have to write out some of the forces in the X, some of the forces in the Y. Just look at the diagram. Stop talking about stocks or whatever you're talking about right now. Stop. 15 kips is pointing up. RBY is 2.5 down. Literally look at the diagram. 15 kips is up. RBY is pulling down. That means the overall force felt by the bridge is 12.5 up. So what does RAY have to be in equilibrium for the bridge? 15 up, 2.5 down. What's missing from RAY for this whole bridge to be in equilibrium? It's just literally algebra, arithmetic at this point. What is it? 12.5, which way?
Down.
15 up.
Down.
Thank you. So 15 is up. This is why I'm saying just make sense of it. It's just logical at this point. The force up is 15. This force is 2.5 down. Sum of the forces should be 0, so this must be missing as 12.5 down. So I can conclude from this that RAY is negative 12.5 kips. Again, it's because it has to be in equilibrium. This is an easy example because the applied force is only in one direction. I don't have to break up the 15 into an x and y component. The 10 kips is only in the x direction. So what do you think RAX is going to be? I'm seeing like 3 people really focusing right now. 3 in the room. Okay, it's the same 3 people. What do you think RAX is going to be in this problem now? 10 kips is pulling to the right. RAX is the only reaction occurring here. Mike? Not 15. X. So we have 10 kips pulling to the right here, right? So it's got to be 10 back. Okay, 10 back. So 15 was pulling up, which is why we had 2.5 down, which left us with 12.5 down. This adds up to 15 pulling down, which balances the 15 pulling up. This 10 to the right has to be balanced with RAX, but which way does RAX have to pull to balance it?
Right.
So what kind of an answer is it going to be then?
Negative.
Okay, so we can then continue to conclude that RAX is negative 10 kips.
Bless you.
Now, that's just the reactions. All we did was the reactions so far. We have to find the structural support in each member. Luckily for us, there's only 3 members. Ernest.
I was gonna ask, couldn't we have already come to that conclusion before, like in the beginning, about RAX?
Absolutely. Absolutely, Ernest. Good point. We're going to talk about that. Very good point. But Ernest, would that help you with RAY?
What? Yeah.
Would that help you with RAY?
If you no, it
What?
wouldn't.
RAY and RBY, our force is only in the y direction, and we have one equation in the y direction. Sum of the forces equals 0, but 2 unknowns, right?
Yeah.
So even if we made that conclusion about RAX to start, we would have had to use the sum of the torques and the sum of the forces in the y to solve for RAY and RBY. Does that make sense?
Yeah.
But I like what you thought, Chris. That's very smart. Because the minute you have a force acting at an angle, then doing what you said is very useful. But these forces are not acting at angles, they're all perpendicular. Understand?
Yeah.
Well done, Chris. It's very smart. It's intuitive if you see it. So we're going to use that in a second. All right, so we've got our reactions. Wonderful. Now, what was the nodal analysis procedure we went through? The reactions are, I think, actually the harder part. The nodal analysis is the easy part. Because the nodal analysis, we're not doing torques. We're only doing sum of the forces in the x, sum of the forces in the y. But how did we approach nodal analysis? What did we do? We isolated one node. And then from that, what do we draw? Look back at your notes if you have to. Some of you did a great job of taking notes last time. Others didn't. So I'm doing this a second time for those others right now, which helping helps.
Free body diagram.
Yeah. We drew a free body diagram of each node. So if I want to, I can start with node A, node B, or node C. It doesn't matter actually right now. It makes no difference which node I start with. I would start with node A. The reason being, the force on member AB, take a look at where I'm pointing. The force from member AB is only in the x direction. Do you see that? That will be very useful in a minute. If I chose node C, I have a force of this member that's in both the y and the x, right? This member is in both the y and the x, but this member is a force pulling to the right, only in the x. So let's choose node A or B, because one of the members connected to it is not at an angle. That is very useful.
At A, if you have RAY. Oh, wait, no.
We know them now. We know them now, RAY and RAX, right? Earlier we didn't know them. Ernest?
But at point C, there's only going to the right 10, so isn't that not...
But look at the members themselves, the members, not the applied forces. These members are not perpendicular to this or acting only in the X or only in the Y. These members are pulling on the node at an angle. You see that?
Yeah.
That's why we're not going to choose C. So let's take a look at node A. Okay, let's take a look at node A. So node A is going to have a force pulling on it this way from that member. It's going to have a reaction RAY, which is down 12.5. So look what I'm doing, everybody. Please recognize. Earlier, the answer for RAY was negative 12.5, wasn't it? So what I'm going to do is I'm going to recognize that negative means it's just pulling down. So I'm going to draw the force at node A from RAY as down. This is node A. This is a force that we don't know. We also have, let me actually do it this way. We also have a force in this member that we don't know. But we do know that RAX is negative 10, so that's this right here. That's everything that's happening, but I need to give names to these Fs. So you just name them based on the members that they're working with. And if I recall, I want to make sure I'm clear. In last class, I wrote it in a way, let me just make sure of this. So here, this is a force acting on node A. That's how I said it. That's right, Ernest. Very good. So acting on node A from what node? Well, this one comes from node C, so I call that FAC. The other one comes from node B. We'll call that FAB. Is that correct?
Yeah.
Based on the arrangement? Okay?
But if you know that it's going to the left, negative 10, then wouldn't it be... Like, because it says going to the right, positive 10. So
Well,
if you
here's
split it for FAB.
the thing. FAC is in both directions, isn't it? FAC is at an angle, isn't it?
Yeah.
So the problem right now is this. FAB is not balancing the negative 10. And I put negative. Sorry, guys, I'm making a typo. That should not say negative. See right there where I'm pointing to?
Yeah.
Oops, if I can point better. That should not say negative right there. Make that a positive because I already drew to the left. I accidentally put a negative there.
Wait, can you not erase?
It's weird. After I stop working in an area and change the tool, I can't erase the older stuff. It's a weird feature of this app. I don't know why. So if I were to right now, watch, and then I go to the eraser tool, it'll erase that. And it literally shows. But if I try to erase the triangle or the RAY, nothing erases over there. I'm trying to right now. Because it's an old image that's in there. It like embeds it as an image after it's done being worked on. It's because I'm changing from tool to tool. I know, Mike. It's really annoying.
What app is it?
It's called Explain Everything. It's actually a phenomenal app. It's wonderful. It's the only downfall. And I've written to them about this. They've made updates in the past. But I like the Notability Eraser better. Although I don't like it sometimes because when you like touch one area, the whole thing erases. And sometimes I don't want that in these diagrams. So it's kind of half and half. Anyway, recognize that FAC is acting at an angle. So FAC is pulling up and to the right. FAB is only pulling to the right. So what we can do is look at the y direction only first, because FAC is the only thing acting in the y direction, and we can easily figure out its value as a result. But the problem is we have to think about trigonometry. So let's take a look at our components here. I drew the triangle on the right for a reason. I did that for a reason. So let's go ahead and drop an altitude in here. It's not drawn perfectly, sorry. Let me draw it nicer. It's a little bit better. Okay, drop an altitude. We know that the dimension here was 10. That was given in the diagram. That was 10. That was 10 right there. Okay, those were all given in the diagram. If this is true, and it's a 10 by 10 by whatever triangle, what must my angles be?
So it's 1...
No, you had it. Say it again.
45,
45, 45, 90. Very good. Be careful. It's not 60. That would be if it were 10 by 10 by 10.
Oh.
This is 20, Mike, right here, right?
Yeah.
It's 20 by whatever. This is 10 root 2, and this is 10 root 2. If you did Pythagorean theorem, right? You'll get 10 root 2 for all those dimensions. So it's not a 60 one. So we have 45, 45, 90 in that sub-triangle. So let's take that knowledge and apply it. Go to your node and draw a 45-degree angle in here. And now it's just basic nodal analysis, which is just a free body diagram. This is literally a repeat of physics last year at this point. Your goal is to find, it's a little harder, obviously, I get it. but it's a repeat in the sense of the fact that it's a free body diagram and two unknowns, and we'll have two equations. So we can do the sum of the forces in the x and the y, both, and we'll guarantee to answer it. But I'm going to start in the y direction. Why? Gus?
Maybe because there's both, it's acting both in the y and the x, so if you solve for one, it would be easier than to solve it for the other.
That is true, but give me more than that. There's something more specific than that. You're right. That is true. Mike?
It's not easier because it uses gravity.
We're not even accounting for gravity with the bridge here, so don't worry about that yet.
It's because of sine is 45, it's easy to calculate.
Well, they're both root 2 over 2, sine of 45 and cosine of 45. But again, recognize that FAC is acting in the y direction, partly, and the x direction, partly. So how many forces are acting in the x direction now? 2. This is FAC in the x direction, and this is FAC in the y direction. There's only one unknown in the y direction. It's FAC in the y direction. Okay, and if you recall, this is just FAC times the sine of the angle. And this guy over here is just FAC times the cosine of the angle. So when I'm doing my equations, and I'm looking at my equations of equilibrium, I could say in the y direction, I've got a negative 12.5, because that's pulling down, and a positive FAC sine 45. And that's in equilibrium, so it's got to equal 0. That's my y equation. There's only one unknown. It's FAC. So as a result, it makes sense to start with the y direction because you can very easily solve in the y direction here. I could solve right now. I'm going to write the x direction down, though. In the x direction, I've got negative 10 kips pulling back. I've got FAB pulling all in the x direction. Again, look at FAB, look at the diagram. It's pulling to the right, so it's only in the x direction. No cosine or sine needed for FAB because it's all in the x. But FAC is partially in the x, so we have to multiply it by cosine 45. But what are we going to notice? If we can get FAC right here, we can take that value, plug it in right here, and then get FAB as a result. It's a lot of subscripts, so it looks more complicated than it is. Okay, so if you're just focusing right now, this should be very simple. We're going to move the 12.5 kips over here as a positive, which yields FAC times 0.7071, or root 2 over 2. I know a lot of you like decimals at this point, and that's fine right now. I don't mind. Divide by 0.7071 on both sides to get FAC. FAC, I don't have it because I did node B first last time, of course. I just happened to choose that. But FAC should be, I don't have a decimal. I left it in radical terms. Ugh. What does it come out to be? Somebody just give me a number, please. 12.5 over 0.7071. Thanks, Mike. It's going to be more than 12.5, I know that.
I got 17.67.
17.6.
All right.
6,
So I'll round to 8 for now. That works. But the answer's positive, right? We got a positive answer,
Yeah.
which means member FAC is in.
Compression.
Positive means
Tension.
tension. Got to memorize that one at this point. The word T starts with the letter T. The word tension starts with the letter T.
Okay.
It's a positive symbol.
Okay.
Does that work?
Yeah.
Remember the whole idea of mnemonics?
Yeah.
What is negative?
Compression. If the we're talking about the members, right? Not the reactions. The member forces. So member FAC is in tension. So if this is your popsicle stick bridge, do popsicle sticks fail easily in tension? No, they're very strong. So you probably don't have to double up this member. Take a look where I'm pointing, right here. Now, this case has a force at the top that's applied up and to the right. You're not going to have that though, right? So this will not be your popsicle stick bridge answer is what I'm saying. You guys need to do this exact thing that we did here, but with a force acting down. One force acting down at the center. And your truss will not be 3 members. You will have more than 3 members. So it will also look different. I'm going to pause. Okay, so back to this. We know FAC is 17.68. Let's use that in the x equation. Just give me I know it's activity, so we're not in that much of a rush. Just give me a number for this if you don't mind. Okay, solve for FAB here. Move the 10 over. Move the 17.68 times 0.7071 over. It's actually going to be 12.5, right? Because it's multiplied by the same number? Yeah. Because we're multiplying by 7071, whereas earlier Mike was dividing for us by 7071. So that'll yield a 2.5. Which gives me FAB equals negative 2.5. So FAB, this is in tension up here. FAB will be in compression. So here's what I want you to do tonight. Do I see you guys tomorrow? Day 3. Yeah? Double, right? Okay, so here's what I want you to do tonight. I want you to do 2 things. 1, finish this example. There's 1 member left. Okay, you can do the nodal analysis at point B. I think that would be best. And then what you do is get at least the reactions done for this. And we'll do the members together then. These members are a little trickier. There's more. But do at least the reactions. You're going to have RAX to find, RAY to find, and RCY to find. Get those reactions done tonight. Okay, I'm going to ask you to turn it in, so put it in your drive folder when you're done with it. Okay, finish up the one we just did, and finish this by getting the reactions tonight for this example. If you decided to read stocks all period, you might need to look at this video. I'll be nice and put it online. It just makes about 4. Okay, again, so starting in the x makes sense because there's only one unknown in the x for the entire bridge. When we get to each individual node, we'll have to look at x and y directions independently and see that, but this is our good starting point. Inigo.
The thing I never understood about this is, so I know that we set it to 0 because it's an equilibrium.
Yep.
But if we are making it for our own bridge, how do we don't know if the bridge can withstand that weight? The whole idea is that you're going to assume it will. That's the whole concept. Okay. So you want to think about how much weight are you going to apply to the bridge? What was the max weight I said in the contest? 100 pounds or something like that, right? So let's say 100 pounds. So you should set up your bridge and draw it with a 100-pound force acting down. Then from that, you can calculate how much force is in each member to see if it'll break or not. That's the whole key, is to figure out where the breaking point will be. So in this process, we're going to find the compressive or tensile strength or resistance in each of these members. And if they exceed the strength of a popsicle stick, it will break at that location. So you know to reinforce that location. So you're not finding out whether or not it's going to break. You're finding out where it will break as a result of the 100-pound force. Because each member has a limit to it. Like steel. Physically, steel, if you look up on a table, has what's called a yield strength. It's the maximum strength you can apply before what will happen actually, the steel will actually stretch like a rubber band. And it will neck. There's a quick, maybe I'll have you do it. You know what I'll do? In the next single period I'll have you guys do it. It's like a quick applet online to do this little thing with tension and torsion and seeing how members fail. So to get the idea of compression and tension a little bit better. But that's what we're looking for in this example. But the assumption is made that the net force has to be 0. So you're always going to set it equal to 0 to start. Equilibrium always. Now, that's the first part I know. So I've got my RAX. Now, if I look at the y direction, the problem right now in the y direction is that RAY and RCY are both unknown. So I can do the sum of the forces in the y direction, and this is what it would look like. It would say the following. RAY plus RCY plus 27, all the y directions, equals 0. But that's 2 variables that I don't know, and only 1 equation additionally. So it's not useful right now to do the sum of the forces in the y direction. It doesn't help me, because again, I don't know either of these. I know that adding these together plus 27 equals 0 in the y direction, but that's 2 variables. So it doesn't help me to start or to go to the y direction next. So if we did the x direction, right, there's 3 options. It's x, it's y, and it's torque. If we did x, and we find out that y isn't going to help us, we have to go to torque.
And the really, really intuitive way to approach torque is to take the torque about a location where most forces are acting. And if I look, these two forces are both acting at point A. So they will not cause any torque. Again, if you're not sure what I'm talking about right now, I forgot about torque, put your pen here, hold your pen or pencil where you're going to put the pivot, and then apply a force. If I apply a force on my thumb, does that cause rotation at all? But this causes rotation, doesn't it? And this force up here is like in the middle, that causes rotation. And if I had a vertical member like this, and I think about this force, that causes rotation. But this force right here, and this force right here, if I push on my thumb here, and push on my thumb, or on the pivot right there, that's not going to cause a rotation if I push on that location. So I'm going to sum the torques. Oops. I'm going to sum the torques at point A. And we're going to say again that it's in rotational equilibrium. Additionally to force equilibrium from the sum of the forces. Now, the question becomes, how do I figure out all these torques? And this is where it gets a little bit tricky, so let's talk about them. So again, RAX and RAY will cause no torque, so I'm not even going to include them. RCY causes a counterclockwise rotation. And if you're not sure, again, the pivot is A. We're going to always pick the one that has the two forces as our pivot, always. It just works this way better. We put our finger here, we apply RCY, and we see which way would this rotate. And as I apply that force up, it rotates in a counterclockwise manner, and counterclockwise is positive torque. Clockwise is negative torque. If you did not remember this from last year in physics, jot it down so you have it written down. Ernest.
I remember for some reason I got that iteration where I did the translation of forces, which you went in a lot of class, and then it ended up working out. Well, I won't say the answer, but
Yeah, translation are what you're going to want to use here for sure. Give me 1 sec to get to that. But you're absolutely right. That's the next part we're going to do. If you remember the formula for torque, it's in the top right here. Tau equals R times F. Now, it's always sine theta, but we are going to translate our forces, like we talked about translation of forces, to avoid any angles for the torques. It makes life a little easier. So I'm going to use R times F and assume the angle is 90 degrees, which it is in this case. Start at A, draw your R value, and there's the force. And that's a 90-degree angle. So RCY is already perpendicular. And I'm going to draw my R value here, and that's a length of 8. So this is going to be a distance again. This is going to be 8 goes in for R in the formula right up here. The force is RCY. So this is going to be, again, and it's going to cause a positive torque. So again, I'm going to start with, again, R is 8 times the force, which is RCY. But then I have to consider the fact that 27 and 18 are also causing torque. Look at the 27 and look at the 18. 27, if I translate the force, this was the key that I talked about that was new to everyone when you do this in physics. If I take 27 and just extend the ray in either direction until it's perpendicular. So I'm going to extend the 27. If I extend it this way, it's never going to be perpendicular to point A. But if I extend 27 this way, take a look at what I'm doing. Extend the 27 this way, eventually it makes a right angle right there.
Do you make it negative then?
So what I do is I don't make it negative. What I do is I just use 27 kilonewtons at a distance of 4 meters. Wherever this extension or translation of the force makes a right angle with the actual A value. So if I went to here, I can see that that's not going to be a right angle. If I went too far down to here, then this is not going to be a right angle. Right? That would be an obtuse angle like that. This is another obtuse angle right here. But if I go all the way to right here, which is the perfect location, that becomes a 90-degree angle, and I happen to have that distance of 4 meters already. So this is a distance of 4 meters with a force of 27 kilonewtons causing rotation this way. Again, causing counterclockwise rotation, which is again positive. So I don't have to make it negative, Mike, to answer your question. Okay, the negative positive only comes from the rotational direction, not the force itself. So, yes?
But at that point, isn't that only halfway to the force RC1 as applied?
Correct. So I'm only going to use a distance of 4 instead of 8 now. Yep, absolutely. But that's going to be a 27 kilonewton force because I already know the value.
But then would you get the 8 RC1?
Wait,
The
isn't
eight-
it 8, not 4?
8 comes from this distance right here. RCY acts a distance of 8 meters from the pivot. But 27 newtons acts at a distance of 4 meters from the pivot. It's always back to wherever you pivot. The pivot point is A. The pivot point will always be the fixed end with 2, right? With 2 of these values on
I
it.
thought you had to use the 8 with the 5 and the 3.
Say again, Mike?
I thought.
We're going to use this 8 right here as well. Yes, we're gonna-
That's for X, right? That's an 18.
Correct, that's for the
Okay.
18. Very good, Mike. Well done. That's going to be for the 18. So let's take the 18 next. I'll use yellow for this. Let's extend the 18. Now, if I extend the 18 this way, it's not going to help me. Look what I'm doing first. I can extend the 18 to the right, but that's never going to be perpendicular to A. Like, watch. Connect from A. Watch what I do. Connect from A to here. That's not perpendicular. Connect A to here. It's still not perpendicular, right? There's my angle. But if I connect A and take A and slide it straight up, and I extend this force to the left, so extend the 18 to the left now, I'll see that at a certain moment in time, this will eventually become a right angle. And that's when it's going to become a right angle. Okay, so look at the right angle in yellow right there. And we can see that there's the right angle. So now we can use the 5 and the 3. Make this look a little nicer. Hold on. Now we can use the 5 and the 3 as our lever arm or as our distance. This here is going to be the overall distance that the 18 newton or kilonewton force is from the rotating axis. So it's rotating about this point. That's a distance of 8 meters. This is causing what kind of a rotation? If I were to think about this member like this now and push it that way, it's still going to cause, positive rotation or counterclockwise rotation. So a distance of 8 meters with a force of 18 is going to be, again, another positive in this case. And this whole thing is going to equal 0. I'm running out of room, so I put it on the next line. But this is all one equation here. So I've got the torque from RCY, the torque from the 27 kilonewton force, and the torque from the 18 kilonewton force. This is pretty far from the fulcrum, 8 meters. This is pretty far. This one was pretty close. And again, that has to do with extending the forces and seeing how far they are.
So the 8 is coming from
5 plus 3. This 8 right here, and then this 8 right here comes from the 4 plus the 4. That's how far RCY is. This is how far the 18 kilonewton force is. That's 8. That's also 8. Okay? They're both 8, but they're different 8s. They come from different locations. If you want to, Jake, maybe do this for now. In your notes, call this 4 plus 4 in parentheses, right? So that later when you look at it, you know where it came from. And call this 5 plus 3 for now. That might make more sense so later on when you see it. You know what I mean? So when you're referring to the diagram to help you with your other problems, you can see where that value came from. Now, what do you notice about this equation? How many unknowns are in the torque equation? Only one. The goal here was to get rid of RAX and RAY by taking the sum of the torques at location A, and we did just that. We got rid of RAX and RAY. So this will give us RCY if we solve it. I don't want to really have to sit here and do the math for it, because this part is just algebra at this point. You got 4.5 for RCY? I think that's RAY you got. Yeah, RCY, I have negative 31.5. You have RAY there, Ernest, I think. It's definitely negative, Ernest, because look at the math, right? This is positive, these are going to be positive numbers, How do I move them over? Subtraction, right? And then I divide by the 8 to get RCY by itself. So the answer's got to be negative. So you did RAY or something else somehow. RCY should come out to be negative 31.5.
Then how do we use this in the Y?
Because in the Y,
You know RCY.
yeah, once you know RCY, you can find RAY. Because they have to add up to 27, which is the unknown force.
Is it
Negative?
31.5.
How could you get negative is the question?
Well, because you have 8 RCY, and you have to move it over to the other side of the equation.
Yeah, so it's got to be negative, right? This is logical. The answer has to be negative here. Because what you're doing in essence, right, is moving this term over, which is positive, this positive. You're taking these positives, adding them up, and moving it over here as a negative, and then divide by 8 to solve for RCY.
For some reason, I had put 18. I made it negative, but I just remember that even though it's forced and it is moving in a negative direction, the negative just shows the sign. It's not
Correct. So that was the mistake there. You heard Ernest said? That's interesting. He made this negative 18 because the force was drawn to the left, and he thought, oh, the force is left, make a negative, when in reality it's the rotation it causes, right? That indicates the sign. But making that negative ends up giving you a different answer. So what I want you to point out or notice now is this. Once we have these unknowns, which we do, right? We've got two unknowns here. We've got RAX now. We can box that in. I should box that in also. It's one of our answers. We've got RAX. We've got RCY. So these two things are now known. The only unknown left is RAY. And again, just use what I'm calling inspection. Inspection. Oh, you got to be able to see it to be inspecting it, right? Come on, have that, please. So RAY acts up. RCY acts up. 27 also acts up. So if I look at the sum of the forces in the y direction, this is a negative, sorry, here it's negative 31.5 plus what number here should give me this balance that we're really looking for in the end. That's really what the question becomes. So you don't actually have to do math. You can, and I'll show you to do math in this one. Sum of the forces in the y is 0. Again, we'll say RAY is unknown. RCY is going to be negative 31.5. And then 27 is acting at the top. So that's my equation, really. Again, RAY is up. That's the positive. This is RCY, which looks like it's up because it's positive, but we got a negative answer, so that goes in for RCY. And then 27 is acting up, so that gets a positive. So I look at this, and I'm going to see here that this is going to be what? Negative 4.5. And then I move it over, which makes it a positive 4.5. So RAY will be positive 4.5. And those are my three reactions for this setup. Okay, those are my three reactions. This is like a third of the way through the problem at this point. The reactions are like the beginning half, beginning third, I should really say. Because we have to do a couple nodes in this problem.
Can you ever try and find RAY with RAX?
Could you find RAY? The only way you could find RAY is if you did the sum of the moments about C, because then this would not create a torque. And this, you have a value already, right? So you could technically solve for this if you wanted to. If you did some of the moments about this. But it doesn't matter. Either direction works. I'm just showing you a technique that will always work. By going X, torques, and then Y is a good approach.
So always go X.
I mean, do whatever's easiest. But in this case, because there's only one unknown in the X, it makes sense to start with the X direction.
I think the shape of it makes it seem much harder, actually.
Say again?
The shape of it makes it seem much harder.
Especially in this problem, because this one is a little bit more complicated. We have a couple angles, right? We're going to have to point out some things real quick that in the next part, we're going to start right now. Take a look at what we have. If I look at this up close, this right here, from here to here, is one angle. This is a whole nother angle from there to there. So this is like alpha, and this whole thing is like beta. We have to consider that this member acts at a pretty big angle right there. This member acts at a lower angle. So we're going to need both of these angles in a little bit. Okay, some of them might be 60. It might be useful if they are, but I don't think for this one they are 60. Right? We're not looking at an equilateral triangle here. We just know that the height and the base are the same. That's all we know. But it's not equilateral, so we can't assume 60 each way.
Well, you couldn't do,
You
no,
can
I
use-
mean, if it wasn't like that, if you could assume that it was 60.
If it was what, Mike? Say it one more time.
If the base was flat. So when that's a little, point without D, let's say that the base was the red.
Yeah, but then this would have to be 8 also. And we're not given that as 8, we're given this as 8, right? See the difference? If this were 8 and the base were 8 and it went across and this were 8, then we'd be 60, 60, 60 for sure. But they're not. They're going to be other angles. I know for a fact. They're going to be some arbitrary lengths. So let's figure out those angles using trig though. Okay, there's an easy way to do this using trig, so we want to figure out what we have here. So when we're looking at the nodes, let's start at node A. At node A, we've got RAX, which we know. We've got RAY, which we also know. We know that we have this force acting and this force acting. Okay, where are those members coming from? Well, this is the force acting on node A from node D. And this is the force acting on node A from node B. So I'm drawing a zoom in or a close-up of this right here. Again, right here. For those that are confused, right here, I've got 1, 2, 3, 4. That's 3 and 4 there. I'm using the letters to designate where they're coming from. Now, RAX and RAY are given values, so I should really just write them down here. Let me jot them in here because I know the values, so I'm going to actually place them.
How would we reference that node? We would just say node A.
I would just call it node. Yeah, so if you want to do like this, go like that to start. Yep.
Alright.
And then RAX, because it's 18 kilonewtons, goes here. RAY we solved, we got 4.5 kilonewtons, that goes here. So I'm going to replace those. I don't have to use the variables anymore, because once I solve for the reactions themselves, I don't have to use RAX, just use the numbers that they are. The issue you're going to run into for this problem is that you have 2 variables to solve for, FAB and FAD. 2 variables means how many equations must you need? 2. So we need the sum of the forces in the x, and we need the sum of the forces in the y. We have to do both equations here. And because we're going to have 2 variables and 2 equations, we're going to have to solve, what do we call that? Solve a system of equations. Good. You said substitution method. Yeah. System of equations. Either with substitution, elimination, or if you recall, if you did this, I don't know if you did this freshman year math, I can show you. If not, you can use what's called a matrix instead. And it allows you to solve a little bit quicker. And I'll show you that. I'll show you how to do that. But the important part is that we see this so far. Now we need to recognize that we have angles. And the angles are going to really be a bit of a hiccup, if you will. Okay, so what I need to do is I'm going to use yellow. Watch what I'm going to do, please. I'm going to designate my lengths. This, from the diagram, is a length of 4. This is a length of 3. Look at where I'm drawing my yellow. Yellow is not forces, yellow are just dimensions. The 4 comes from the diagram here, and the 3 comes from the side right there. Because the 3 and the 4 make sense. Pull them from the diagram. And again, I'm looking at this height right here. That's a height of 3, and this is a length of 4 as a base. So 4 by 3 by whatever the rectangle, the triangle's hypotenuse. What would the hypotenuse be then? 5, because it's a 3, 4, 5 right triangle. Okay, I don't really need the hypotenuse though, just so we're aware. I actually don't need the hypotenuse, but I can write it in as a 5 for now. That's the length. Then I'm going to use green, and this is going to be tough because they're going to overlap a little bit. I'll try and zoom in a minute. But I'm going to use green now to draw my triangle for FAB. I'm going to use green, to draw my triangle for FAB. And it's kind of hard to see that one. Okay, but there's the triangle for FAB. And this one was 4 and 3 and 5. I go back to my original diagram to see what those heights are. Let's go back and see, where does FAB extend? Well, the full height is going to be 8. Because this is 5 plus 3 on the side over here. That'll give me an 8. That'll be the height of this green triangle. So the height is going to be 8 right there. The base,
Isn't it four?
yeah, it's still going to be 4. Okay, the base is still going to be 4 in this case. Doesn't look like it based on the drawing in my diagram, right? It's not obvious, but this is also 4. Okay? So I know they're not drawn to scale. Ignore the triangles being drawn to scale. I know that this is 4 and this is 8, and I can figure out the angle that I'm going to need in a minute. This is 4 and this is 3, and I can figure out this angle in a minute. Okay? Yes?
Why don't you just, like, just not say page, like, we already did draw a right triangle first. When we did the first 3 block diagrams, let me just use that. To highlight that it was 8.
You could draw your triangles anywhere. I don't have to draw. I'm drawing the triangles on here right now to show you, but I could have drawn the triangles on the side and used them. That's fine. Absolutely. The key is this, Ernest. We need to figure out the angle in green, which is this angle right here. We also need to figure out this little angle in yellow, which is going to be this angle here. So either way, I'm doing opposite, and adjacent. What trig function do I use for opposite and adjacent? Tangent. So I can say that the tangent of the angle in green is equal to the opposite over its adjacent. Again, that will give me this angle right here in green that I'm drawing in. That'll give me the angle between the horizontal and FAB. The horizontal and FAB. That's the angle I need to find first. So let's do the tangent inverse of 8 over 4 to give us the angle. All right, the tangent inverse of 8 over 4. I don't have a number in front of me. If you can give me a number, please. 63.4 sounds right. But I also need the other angle between the blue vector right here and the horizontal. I need this angle also. Remember, I need the angle that measures up to the vector. I need this angle, this little guy. And that's going to be tangent inverse of 3 over 4. Right? 3 over 4 instead of 8 over 4. The 5, again, doesn't matter. 5 has no significance. So the yellow angle, one second. The yellow angle, we use this equation to get its theta. Thank you, Mike. So that's going to be this angle right here that I'm about to draw in yellow. Okay? Again, that's the angle from here to here is 36.8, and this one has to be bigger. Okay? The green one has to be bigger than what we're getting in yellow here as an answer. It's not double or anything like that. It's just they're arbitrary. They're not one's double the other. Okay? Now, once I have the angles, I can do my sum of the forces, but that just took a while to do that. You can see, right? So it is going to be messy. It's not an easy process to go through. There's a decent amount of trig involved. But now that I've got all my angles, what I can do is I can kind of redraw my diagram with my angles in properly. So that's 18. That's 4.5. I'm going to put a little dashed line as a reference line only. This angle here is 36.8 degrees. And then the next angle is this big guy here. And that's an angle of 63.4 degrees. Okay, again, this is still FAB right here. And this vector, it's hard to draw right now, is still FAD. So all I'm doing is redrawing this diagram so it looks a little bit neater without all my triangles, so you can see it a little bit better. But the key is to recognize that we still have an unknown force here and an unknown force right here. Okay, again, this is still node A. I want you to see that I'm just redrawing the diagram below the squiggly line. I just redrew the diagram. So if I take a look at my sum of the forces and start in the x direction, in the x direction I've got 18 automatically because that's going to act to the right. Sum of the forces in the x, 18 starts. FAD is acting to the right and up. Again, FAD is acting to the right and it's acting up. So to the right, I can take FAD times the cosine of the angle. Whenever I want the x component, I take the actual vector times the cosine of whatever the angle is, in this case 36.8.
And then to that, I'm going to add FAB times the cosine of its angle. And its angle is 63.4 degrees. And that whole thing is equal to 0. The equation's kind of wrong, sorry. 18 plus FAB cos this plus FAB cos this equals 0. This is the sum of the forces in the x direction. And then I need to do the sum of the forces in the y direction. But what I want you to pick up on is recognizing that you cannot solve for FAB. You cannot solve for FAB. They're both unknown here. So I need to go to the y direction and use the 4.5 and use the y component of FAB and the y component of FAD to come up with the sum of the forces in the y direction. I've got 4.5 acting upward. I've got FAD again, but only the y component, so I'm going to take the sine of the angle now. And then to that, I'm going to add on FAB times the sine of its angle. And again, that whole thing equals 0. So this is one equation right here. And this is going to be the second equation right here. That's a plus sign. That's a plus sign. So what this will do is this will give me two equations with a lot of variables, or two variables in this case, and a lot of decimal coefficients. It's just a matter of, solving a system of equations at this point. I think I have some decimals written down. I do. So we've got the first equation, cosine of 36.8, I wrote down is around 0.8. So I've got for the first equation over here, 18 plus 0.8 FAD plus, the other one I wrote down 0.447. And that's times FAB. So this equation, again, two unknowns, cannot be solved. This equation is going to be the same idea. We need decimals again. The 4.5 carries down. Aside from that, we have FAD times 0.6, approximately. And FAB times 0.894. So again, it's the same equations, just continuing down. And what we're noticing here is we have a system of equations. We've got two unknowns in both spots, and we've got two equations. You could solve for FAB here, right, in terms of the other variables, and then plug it in for FAB over there. And that'll get rid of substitution method. And if you feel confident in substitution method, I would recommend just continuing using that. You could use elimination method, but elimination can be a little bit trickier for some students, so I think substitution is actually easier. So let's solve the left-hand side equation for FAB over here. FAB will be negative 18 minus 0.8 FAD all over 0.447. Okay, if it's not clear to you, you got to work on algebra skills a little bit. This is not a hard thing to do. Take 18 as a positive, move it over, it becomes negative. Take 0.8 FAD as a positive, move it over, it becomes negative 0.8 FAD. How do you get rid of a coefficient that's left now? Divide by 0.447, divide by 0.447. That is FAB. You can take that expression and plug it in right there. What will that do? That'll allow us to solve for FAD. And then once we know FAD, we go back and find FAB. Okay, there's a lot of work to these problems. I know it's not easy. Okay, it's definitely not easy to go through this, but it will take you, this would take like a solid full period to solve one problem. Would be my ideal timing-wise, right?
You know, if you actually didn't stop and show all the steps and did the work quickly like you should do it, it'll take you like a full period to get through the whole thing. So this equation becomes, let's see, 4.5 plus 0.6 FAD. And then the rest of this is just going to be messy.
Wait, what do you set that to?
So we're going to plug in the whole thing and it's still equal to 0. So it still equals 0 on the right-hand side there. But what goes in that parentheses is that entire expression. And it's just messy. A lot of algebra that's going on here. This is an AD, by the way. That should say AD. I should fill that in. So right now, at this point, you've got what looks like you had two equations using substitution. Plugging into the second equation from the first, you now get a new equation with only FAD and 2 spots missing. Here you have to divide the 0.447 into both. And you have to take the 894 and distribute it to both, or you can just take a look at these first maybe. Right? Do 894 over 447. See what that turns out to be? 894 over 447, and then distribute it to both of those terms.
Oh, 2.
It's just 2, right? It should be, yeah. It should work out to be 2 there.
Is this the most difficult or
Yeah, I mean, this is the hardest you're going to see on like an actual assessment. I'm thinking I'll give you guys the assessment, not in the next single, but the single after that. I'd like to give you before the end of the quarter for sure. So again, what I did was here, I recognized that 894 divided by 447 is just 2. So I just combine these two by dividing these first with a 2, and then take the 2 and distribute it to both of these terms. That'll become a negative 36. That'll become a negative 1.6 FAD. Combine that with positive 0.6 FAD as like terms. Negative 36 and the 4.5, combine those, move them over, solve for FAD. Okay, FAD will come out to be, I don't have it written down, let me see. FAD turns out to be negative 31.5. And that's just, it's not, let me see, FAD, let me see where that is. Yeah, it's not any significance that had the same number as an earlier number, right? We had negative 31.5 earlier as one of our answers. What does it mean that we got an answer for one of our members that's negative? What does that mean about that member? We made a conclusion at the end. If it was a negative answer, the member must be in compression. Okay, remember the positive sign looks like a letter T for tension. That's why I had you guys remember that. If you get a positive answer for one of your member forces, it means it's in tension. The negative answer means it's in compression. In compression, like.
When we're doing this for our bridges,
Mhm.
how do we analyze it in the kind of 3 dimensions? Because
You don't. You only look at a 2-dimensional structure from the side. That's it.
Alright.
Yeah, I know. There's no 3 dimensions. You're honestly just what you're doing is you're analyzing one side of the truss really, and by having a second side and having the plates that connect, it's a stronger bridge as a result. But you're not analyzing the full 3 dimensions here. This is only a 2-dimensional. It's called planar truss structures. Planar, like a one plane. So it's only 2-dimensional beams. Yeah, it's a good question. You can't incorporate the other side. So that's FAD. Once you get FAD, you can plug that in here or here. Either spot. If you plug FAD in here, you get FAB. If you plug FAB in over here, you get FAB. So once you get one of the members, go ahead and plug it in to get the other one. And that'll yield FAB of 16.1. Again, take this number and plug it in either here or over here. Or actually, honestly, the best spot to plug it in would really be to plug it in right there. Is that what you're going to say? Yeah, that's actually the most logical. Because you've already solved for FAB. You have an expression for it. So plug it in there, and you'll get, and I saw your hand, Ernest, that's what made me think of that, so thank you. 16.1 kilonewtons. So FAB is in tension, whereas FAD is in compression. Unfortunately for this bridge, we can't use symmetry because we don't have symmetric loading. If there was only a load acting vertically at the top, you could assume that both sides are identical. So these answers you got for these, you could use the exact same answers for the other two members. You know, the whole shape is like this. This is one half of the truss. This is the other half of the truss. They meet in the middle. If there was only a vertical force acting, only a vertical force acting, and only acting at the middle point, you could assume symmetry on both sides there. Okay, you could assume symmetry there. But we're not going to have symmetry in this problem. So we'd have to work our way around the rest of the nodes. We only have about 2 or 3 minutes left, so I want to just point out where you would go next with this. So let's go back up to the original. I know some of you are writing the numbers. I'm going to come back to it in a second. Go back to the original now. We have now, let's just check off what we've done. Let's put little check marks. We got RAX, we got RAY, we got RCY. Those are done. Right? These three unknowns were the starting points. We then found out FAD and FAB. So that means that we've got these two right here and here. So we still need to get this one right here, which we can easily do. We still need to get this one right here, and we need to get this one right here. Okay, we still need to get members 1, 2, and 3. And we can do that by looking at the sum of the forces at this node where there's two unknowns. We could do the sum of the forces at this node where there's two unknowns. Or the sum of the forces at this node where there are still 1, 2 unknowns. Just however many unknowns are attached to that node is what matters. This is known. This is now known. These are givens in a sense. We determined them in the last part. So these are the ones we want to find out. Try to practice finishing this on your own. Okay, I'm going to see you guys tomorrow in class, but try to consider practicing the rest of this tonight to go through and solve for the rest of the actual truss structure.